Yes. And now what would be smooth ground? Very nice. Yes, the expertly placed right here. So a ground that this sees would be a ground basically anywhere in the system. All right, cool. So we can get on to this guy here. And if you take a closer look, if you come up here, Greg, or whatever, you'll see that there is some kind of material applied to this one that, while not being...
That magnet wire has a little coating on it,
yeah,
so you
some
sand
kind
it
of
off
varnish
at
or
the
something
end.
like that. Yeah, so it's got a little bit of insulating properties, but obviously not part of the main insulation, which would be these guys, right? So this is protecting your face to face, and then
But you're clamped onto a part where you sanded it off or scraped it off or something.
Yep, and so that's why we have ideally a better connection. Who knows? We'll find out. That is the scientific. A little bit, so better get a bite on it. And what is our test KV? 500. We're in the big leagues.
Wait, what was the motor rated for? What did you say?
We're going to treat it as good up to 5 kV. And so our 41.
By the table, it looked like it's about half of what it's rated for.
Okay.
Would be my guess, like on the table.
Hopefully in the real world. Yeah. And so let me zoom out just a little bit. So you can see here we've got 2.5 kV, 2,500. We're testing for 1 minute. Is that what we're going to do this class? Or are we going to test for how long? 10 minutes. 10 minutes. And the nice thing is, on these modern units, it's a little bit tougher to see. Man, Intelligent's giving us the good stuff. This actually has a dedicated mode for polarization index. So this one, I'll read it out for you since it's a little unclear. Here's IR, just for insulation resistance, with no predetermined time. So this one will just kind of run endlessly and like good for spot checks or until you feel like it's an acceptable passing value. Right now, we're usually on the IR with T in parentheses, so insulation resistance as a function of time. This is the one that defaults to 1 minute. Remember, we like the reproducible, consistent 1 minute test. This one says DAR. What does DAR stand for? Dielectric absorption ratio. Bingo. And that is which value divided by which value?
1 minute and 30 seconds.
Excellent, excellent. And if it's good insulation, is it greater than or less than 1? Definitely. All right, I'm liking what I'm hearing. All right, now we're on PI. PI stands for polarization index, of course. So what is our time value we're seeing in the bottom left corner? 10 minutes, cool. And so what we're going to do here is we're going to run the test, and we're also going to write down our values. I'm going to write it down here. Also, you should record it on your papers as well. And we're going to see how this performs. Eventually, we're going to calculate these numbers and see what we can figure out about the health of this installation. I'm going to prop this up just so that there's no funky business going on the table in terms of shorts, unintended shorts, etc. All right. So now this should be pretty good. All right. So we'll see how this thing does. And remember, stay tuned. I know it might pass pretty quick for the first two at least, but we're going to record those values. All right. So if we're clear on that, 2.5 kV for up to 10 minutes, looking for the polarization index. Cool, thumbs up, good to go, testing. All right, cool. And so we know we're hot because red light's going.
And it just dumps 2.5 kV straight into it. It doesn't like ramp
All right,
it up
we are
over 10 or...
That's no fun. Say it again.
It just dumps the 2.5 kV right off the bat. It doesn't...
It builds,
like,
and you'll
slowly.
notice that the number doesn't quite appear for a while until...
How long does it take to build?
If you remember the capacitive current, the charging current, that one messy
Yeah.
chart in the Megger stitch in time, it would be until it is able to produce that calculation that it'll display that. So it varies, and the reason why, for example, we're doing polarization index on a guy like this and not the small breaker, this small CT, is because what you can see visually, and again, if this was 4160, there's just so much more insulation for it to push through, right? And so, if you recall from the Megger stitch time, when you do a DC insulation test, you're actually kind of turning the subatomic particles, right? And you're shifting your electrons and basically orienting them one way as you're charging and testing the insulation. And so that being the case, if there's much more insulation, well, there's a lot more electrons and stuff. So that's kind of the idea behind that. All right, so let's figure out what's going on here, see if we can get an actual value. Our fun must be messing with it. All right, here we go. All right, testing, try that again. We've seen that test. Man, all right, so somebody must have hit this with that Dawn power clean from last week. Let's look at it. Something is making contact. There we go. Just gonna tie these together.
Power cleans and that's the stuff, dude.
Gift that keeps on giving from last week's lab. All right, testing. Maybe. Okay, so we're starting to build something. Let's lower the voltage just in case. Let's go to 1 kV, see if that, and you can see a difference if it does build. Well, there's clearly a difference as to if we should use more voltage to push through to expose any kind of deficiencies. But here, just for the purpose of getting a reading, let's give it a go. Testing. All right, well, this one seemed to build, or not. Man, the suspense is killing me. Let's do it at 250, and then just like the water hose, what do you call it? Garden hose example, with less pressure, you're not going to expose those pinhole pricks. But again, there's a reason why these test KVs are specified in the book, because for a certain size equipment, you have to stress it to a certain degree in order to expose faults. So clearly, I will not be in any rush to fire this thing up at any factory, right? So that being the case, in this control environment, we're going to push it down to 250 and see if we can't just get this to produce us numbers for the purposes of this exercise. Testing. All right, cool. So artificial scenario here, but good for our purposes, which our main goal is to get these numbers here. So Jeff, to answer your question, luckily the numbers appeared before 30 seconds, because we'd be hard pressed to perform our dielectric absorption if we didn't have these numbers.
What did we lower it to, 1,000 volts?
250, just 250, just to get a number on it. So coming 25 seconds, 26, call out what you see, 29, coming up 30. So like 7.26, anybody else see that? 7.26. So we're gonna let that go until 1 minute. Oh, this is turning out to be a really good example. 50 seconds.
A minute, 4.9 kilograms.
4.98. There you go. Cool. All right, so we have two pieces of information, our 30-second and our 1 minute. I've just been doing things for consistency. Kind of a stickler for that, I guess. 7.26. 7.26. Here you go. All right, so there's a 30-second. So I'm seeing that you're already seeing a trend, right? So we're going to let that go. Let's calculate. We have enough to calculate which value?
0.
Yeah. So let's go ahead and do that. That is which divided by which between these
1
two?
minute over 30.
Cool.
Yeah.
So 4.98 gigohms divided by 7.26 gigohms. Gigohms over gigohms cancel, right? Unitless number, so it only shows a relationship. Remember, dielectric absorption is not an ohm value. It is not your resistance. So if we see, hopefully we don't see in any submissions that your dielectric absorption is 1.7 ohms. That's not true, right? So go ahead and plug this into your calculators and let me know what we get.
0.6859.
0.689.
59.
6859. I'll take 686. Cool. All right. So greater than 1, less than 1. So what does that mean? That means that our chart did something like this. Tank at some point, right? No bueno. Write that on the test board. Well, better like we'll see you next semester. Right? All right, cool. So we'll let that one run. And so this is turning out to be a really good example because we saw that when we pushed, meaningful voltage, right? That this is actually, there's obviously some kind of flaw, in this equipment. First and foremost, there's a layer of dirt on it, right? And so we know that could produce that unintended path, right? To short out from your face to ground, right? So plenty of surface contamination for it to provide that unintended path. That Dawn power wash could be lingering. Man, that thing's haunting you for the last week, right? And so something's up with this one. And so even when we push it to the prescribed 2.5 or even 1 kV, it would have already failed it off the bat, right? But now since we're able to get numbers, again, for the purpose of this exercise, we're already coming to that same conclusion that something about this insulation system is no bueno. That's the key word of the day, right?
And it's
So,
dropping.
yeah, it keeps dropping. So what do we anticipate about greater than less than 1 for when it comes to the 10-minute test?
Yes.
Yeah, and so it looks like if it's on the same path, this thing is even no bueno-er. Write that on your test.
Bueno-er.
Bueno-er. All right, so we'll let that roll. All right. And what we're gonna see, I'll flip.
Maybe the guard will solve all of our problems.
Yeah, very much good. You see, somebody's applying his lessons from last week. That's what we like to see. So, yeah, remember, so as a needed qualified technician, is your first instinct going to be to fail this guy? No, I mean, the test results fail, right? But we're not so quick to fail as we are to say, okay, hey, what does this system actually look like? What is, the possible reason for that? And so my, initial physical and mechanical evaluation, which again, need MTS, so it's physical mechanical, and then you'll do further electrical testing. And again, these layers of caked on dirt that could provide an unintended path. And if you were to clean this thing out, right, use various methods to clean the windings.
Just not power wash.
Don't power wash. Sponsored by Dawn. No, don't deal with it. We like Simple Green, right, Jeff? We don't like Dawn. Not anymore. So, yeah, we clean this guy off, make sure that the environment is not causing undue influence on this guy, so that when we're testing the insulation, just like last week's guard terminal, that we're testing what we actually mean to test, right? If we're looking for the quality of the insulation, let's look at the quality of the insulation, right? Take the environment, take the surface contamination out of the equation, right? That's why clean, dry, happy equipment is the kind that's going to test better for sure. And then we'd be able to, with further investigation, further digging, be able to determine what's causing our kind of failed results. Right? And then ideally, it would show this kind of curve that we're looking for. Right? So that's not the case this time, but we will be testing cable specimens today that should, by all means, exhibit this good, this good kind of curve that we're looking for. Okay. Yes, Jeff.
So we're running at 250 volts, right?
250 volt.
Would that, based off the table here, would that be allowable?
The important thing to note is we already saw that this thing failed when we tried to put it to what the table wanted. So the 250, we wouldn't do in the real world. I'm only doing this for my purposes, right? And for the purposes of this class, so we can generate some numbers, right? So yeah, take this with a grain of salt. This would be automatically failing equipment, right? So great question. In case I didn't make that clear, that definitely this 250 is not unapplicable, not a NETA sanctioned kind of test. What do you got, Jason?
So
I'll get to you
if it would automatically fail, would you like retest it again just to like, oh, maybe it was a faulty test?
Yeah, get another meter, get another instrument. Yeah, you're thinking right along the right lines. This one in this case, luckily, is if I did already have it plugged in, well, I'd say okay, maybe the battery's kind of wonky right now, so I want to make sure that I have a fully powered unit. Maybe try another manufacturer, that kind of thing. But after that, once you're sure the instrument's working, right? Let's maybe get a second set of eyes, because hey, listen, human error, right? We already talked about that in NFPSMD. I mean, the first to say like, yeah, I probably screwed something up, right? Probably done power wash. But then after that, you would apply cleaning surface contamination and making sure that that's not throwing off your data. Which, in my kind of experience, likely, we clean this thing up, it's going to test great. Mario, question.
Since we tested, I'm trying to look for the test that we did on Thursday.
Huh?
That it was more like a pass-no pass. And
Yeah.
we tested one.
The high five.
High five.
That is the guy. So this one, as a time-based test, the pass no pass will be dependent on what is the acceptable minimum, right? Like we've seen 100.1 and now we're seeing 100.11. So the go no go, pass no pass is just did it break down, right? In this case it did. I mean when we use the real voltage, but in this case we actually care about the performance over time, and we'll have a final value that we can say did it meet the minimum. Now here's the interesting part. What was the minimum acceptable value? I mean, even if we push the 2.5, if it didn't break down, what does it say in your 100.11?
It's like 100 ohms or 100 mega ohm?
100 big ohms. What do you think? It actually passes with flying colors, right? But again, knowing that this is an artificial test set, right? What NIDA determines is a suitable stress, electrical stress, to show you, any possible deficiencies in this guy is at least 1,000, right? Much less 2,500. And it's saying that it had dielectric breakdown. We saw the BRD. Right? And so again, artificial test setup, and you should be especially wary because this will look like a pass for your unexperienced, your non-NIDA certified. The guys who get out here without taking this class, they'll say, "Oh, I built it 250 and it's in the gauge. This is a pass. Fire it up. Let's make ice cream. Big money." All right. So, but in that case, it would only be a matter of time before this guy would experience dielectric breakdown in the field. So we're seeing that it's kind of, pretty much been settling at about the same number for a while now. It's going to settle on our 10, but definitely we're seeing this kind of degrading pattern here. So this is telling us that something's up with this one. So that one's going to be coming up pretty soon. So in preparation for that, what are the two values we're going to pull in order to calculate our polarization index?
10 minutes and 1 minute.
Yeah, 10 minutes to 1 minute. We'll leave that top numerator empty for now, but what will be our denominator here? 4.98 gigohms. All right, we'll see how we do, but we're already getting a feeling for how this number is going to end up. Cool, gigohms. So gigohms over gigohms, again, those cancel, you get this number. This is purely a relationship on these two time values. What kind of number are we looking at here? Greater than, less than 1? Way less than 1, yeah. So, no bueno-er. What do you got for
0.31.
Sean?
Yeah, it's about 0.31.
0.31, man. 0.31. So there are two values. So, if nothing else, we had some good experience actually acquiring real-world data, right? From being able to pull up real-world numbers, right? Being able to calculate real-world relationships, okay? And so next time you get a phone interview, you'll be able to say, "Hey, Megger deal on polarization index, dielectric absorption, retroencrabulator," that kind of thing. And then they'll say, "Forget the test, you're hired." Cool. Any questions on this so far? Yeah. What's what? On the Megger, it looked like BR.D. This one, breakdown. And then, I'll demonstrate this just for funsies. I'm going to crank that to 2.5 again. And see, again, your qualified NIDA test technician would know that 250 is not suitable for a quote-unquote 4160 machine. You have to apply an appropriate electrical stress in order to actually show what the problems are. Again, if you have a garden hose with little pinpricks in it, unless you crank that up in pressure, you're never going to find those. Right? So testing, and we are going to see what we anticipate right now. So, hey, I thought it was 1.542 gigs. What's up with that? Now it says our 10 k ohm, right? And where have we seen this again? The less than symbol, less than 10 k ohms. Where have we seen this particular value pop up? Where have we seen it? Where it's been?
Oh, sure.
Sure, exactly. That's why we do the shorted test, right? The open, the closed, and the known resistance, because we know that this, and like Jason was saying, how do we know the test system is working? Having done our open, closed, and known resistance test, we know there's a good working unit. And so if it's seeing less than 10 k ohms, that doesn't mean that it's 9,998 ohms, because that's a pretty good reading. But it means that this is what a Megger will classify as a short circuit condition. Right? And so we're seeing the BR.D, our breakdown, our insulation breakdown, which means that this is not going to do the job, unfortunately. So, but yeah, for our intents and purposes here, we were able to calculate our dielectric absorption and our polarization index. And this will come into play when all of you at your respective stations are going to end up performing that for a cable, because this will be cable. All right, cool. Yeah, so moving right along, we'll go back to our slides. I have these notes handy because you can reference those in the same way during the lab session today. And there's our example. Unless you use a suitable test voltage, you're never going to expose a water leak. Same deal. Unless you're using a suitable voltage, which we know is electrical pressure, you will never be able to expose glaring issues like in this guy here. So just to show you, this is the chart, Jeff, that we were talking about, how long it may take for it to produce that value. So this is just a matter of decimals of a second up to 10 seconds. Hopefully you had been able to stabilize by 10 seconds, so hopefully we'll show by then. But we know when we press the big red button, yellow testing, that it takes a while for it to build voltage and then be able to measure those various currents and how they interact with the insulation system. Cool. All right. And this is our classic, I like my drawing better as usual. So this is our classic kind of good insulation curve, right? And examples of this will be downward trending data, right? To be able to say either for this is a 10-minute test, but over months of a period of time, you're able to say, hey, let's during the next scheduled outage, give further attention to this, repair, replace, refurbish. So just for examples, again, Megger station time is definitely excellent reference for us in this class. So that condition of insulation indicated by dielectric absorption ratio. Right. So what would we say? Again, in your comments deficiency section, you want to have a nice write-up because this is what's presented to the customer, right? You state your reputation on it, and your expertise speaks to it. Our value for the dielectric absorption was 0.686. Where does that fall into here? Dangerous. All right, because it is less than 1. So definitely your write-ups to the customer to say, according to the dielectric absorption ratio, we do not recommend re-energization, or we do not recommend installation at this time if it's pulled up off the shelf. We do not recommend application of this particular unit, right? And you'll be able to support that with the numbers that you yourself generate. And so we'll do the same thing for polarization index. We have a similar same thing would happen. Dangerous, no bueno word, right? So, but we'll take a look at a chart for the polarization index a little bit later. Cool. All right, so that's that one so far, and that'll be the focus of today's lab. We're going to talk about VLF testing. Again, we're in the big leagues. Midterm's over. VLF stands for very low frequency. Excellent. Yeah, and so this is going to be the higher end of the testing. Again, we could bring in a VLF test set so we can see it in action, but as we talk about VLF, very low frequency testing, as we talk about PD, which is our partial discharge, we're talking about very specific sectors of high voltage testing. And again, if you become a very highly skilled, highly qualified expert at this, you punch your own ticket. You're going to be a wanted man in this industry where we already know job security is the name of the game. So we're going to talk about the basics of these various topics. We're going to introduce them to you. And again, in the span of this class, while meeting all of our other requirements, we can only go so far into it, but we definitely want you to lead with the basics and to know where it stands in industry as a very powerful tool in your toolbox, right, for testing. So the IEEE 400 series, while that's not part of the text in this course, as we use the NETA MTS, IEEE 400 series, which is all about cable testing, and the NETA MTS in the past 2 editions have become very, very in line. So you're going to see very similar tables in your NETA MTS. In fact, I'll turn to them now because we might as well look at that exactly. But in the back of your book, and the nice thing is that even when we first started teaching this class, these weren't in line with IEEE, right? There were some different looking standards.
Neil, when you guys are testing stuff, do you always use the minimum
Do we always use
value, like on?
unless the customer will want otherwise.
Okay.
Customer's always right. So at times, for example, for acceptance testing, we'll run things that actually pretty recently, maybe I'll pull up some pictures later, we were testing a 60.5 kV recloser that goes up on a pole, and we were supposed to high pod it at about 60. The customer's like, no, we're good at operating 30 or 35.5. So we ended up high podding to, I believe, 35.5 rather than pushing it to 60. Customer's always right. So, but that would have been fun. I would have had more fun pushing it to 60,000 volts. But yeah, hopefully that answers your question. Yeah. All right, cool.
Table 6.3.
106? 106? Excellent. Okay. So here's our VLF values, right? Nice and fine. And we're going to see, according to the voltage face to phase, kV RMS, we are going to have what the suitable kV for testing. So, so in line with the 400 series here, you're going to see that these also go by RMS voltage and kV, right? But you're going to notice 3 different columns here. You're not going to see, because MTS is only going to have the one column, maintenance, of course, because MTS stands for maintenance specification. But if you were to look in acceptance testing, it goes by something completely different. And by now, hopefully all of you have a good grasp on that the acceptance testing should be a higher value, right? Because it's right out the factory. It should, as you saw, if it's not used, right, new car rolling off the lot, it should be able to take much more of a beating than the kind that's been in service. Again, in service, service age cable, the hot topic of previous classes, right? So, in this case, looking at VLF, you saw 0.1 was in our other, 0.1 hertz. 0.1 hertz, that means that is a very long sine wave. Usually our equipment here in this country of ours operates at what hertz? What frequency? 60 hertz. So that means 60 times in the span of 1 second, you're going to see these sine waves, right? So 0.1 hertz, that means that for basically, you get a sine wave in a second, right? And when it gets even slower than that, that means that you get really, really long sine waves per hertz. Right? So definitely different from what we're used to. And what does this mean for the health of the cable, or what the cables see, right? So that's what we're going to talk about right now. One thing I do want to note is that VLF, which you were correct on this number. There we go. VLF stands for very low frequency. It is important to note the distinction that VLF itself is not a test. Like you're not going to say, okay, I'm going to go VLF that cable. It's a test mode, like a test methodology, right? It's the way you test the cable, right? It's not an actual test. And the actual tests you're going to perform are going to be, for example, your VLF 10 delta, right? VLF is the mode at which you test it, which means not at 60 hertz, right? VLF will mean you'll subject it to 0.1 hertz, but the actual test you're going to perform is the 10 delta test. And so, question? Just bear with me on this. So VLF itself is not a test. You can't say, okay, I'm going to go VLF that, because that just means I'm going to use 0.1 hertz instead of 60. But then the question still remains, what is the test you're doing? So VLF is like your test method, right? So 10 delta will be your actual test. We're going to talk about that right now. So we mentioned before in class that a cable is really just a big capacitor, right? Because it's just a bunch of insulation and a conductor, right? And we know that the way those interact just acts as a huge capacitor. So we're not going to get too, well, we'll get kind of into this, at least for the purposes of your quiz, but for kind of your foundational knowledge on what 10 delta testing is, we're seeing familiar terms here such as our voltage, right? And our current and a capacitor. So this is actually representing a cable, right? Or really most test instruments, but in 265 we're going to treat it as our cable. All right. So a good cable, right when it comes out of the factory, almost acts as a pure capacitor, right? Pure capacitor. So you'll see that there's no resistive component on here. But as the cable becomes service age, as deterioration, use over time, you'll see that there is now a resistive component, right? We'll see that. You can also see it as that, this kind of symbol here. You'll see it represented like that as a resistor. But over time, it develops a resistive component, and we know that resistance also accompanies what? Heat, yeah, under heat. Yep, heat, breakdown, basically wasted efficiency, right? That's been a part of our DLRO module, right? So unwanted, heat loss means system inefficiency, which means possible, places for failure eventually, right? So service age cable will eventually exhibit a resistive component, right? So as a pure capacitor, there's no resistive component, so you're having a 90-degree phase separation, right? So this is ideally what you want, but over time it'll develop this quantity here. So this causes a shift from your pure 90-degree angle to less than 90 degrees here. So tan delta, we know that delta is the Greek symbol here, in this case lowercase d delta. So this is the angle we're looking at. All right, so what's the point of all this? Well, if you are able to determine that angle, this is also called loss angle or dissipation factor, what this tells you is the relationship between the capacitive capability of the cable as well as the resistive. Right, and so this will tell you, it'll give you a clue as to the aging characteristics of your cable, right? It'll give you a clue as to, is it losing, basically efficiency, right? Is it at risk of breakdown, right? And so again, just like we saw with our PI, this tan delta unitless number is just going to tell us a relationship between the resistive and the capacitive components of the cable. And that's what it will most simply go down. So we talked about new versus service age cable, and this is going to nicely tie together what we just talked about. New cable approaches the properties of a perfect capacitor. As cable ages, it deteriorates the resistive component of the cable increases, as we saw on that right-hand side. Service age cable has both a resistive and capacitive component, and tan delta testing helps determine the quality of the insulation. Quality, again, comparing the resistive versus capacitive qualities of the, in this case, cable. So, and you're going to see that on your quiz. Again, refer to these notes as you go along, and you'll be able to navigate just fine through that one. And so, to explain the point of what is the point of VLF testing, right? You could tan delta cable at power frequency, I guess, but what is the advantage of performing a VLF?
Doesn't stress it as much as a high pot,
Definitely.
right?
Yeah. A DC high pop for sure is going to kind of mess with those space charges, right? And accelerate water treating and eventual breakdown. But even the AC component, which is again 60 times per second, this one is a long drawn out sine wave, right? If you look at it mathematically, right, we know our 2 pi f, that's our capacitive and resistive. Our f frequency is the one we're changing, right? We can't do much about, 2 pi is our constant, right? Our capacitive and resistance, parts are what we're actually looking for, right? So what are we free to deal with? The frequency. So instead of 60, we're able to turn that into 0.01, right? So you're seeing that, less than basically 600 times more manageable in that. The advantage of doing this, so the tan delta test itself is to, again, look at the quality of your insulation in terms of comparing your resistive versus your capacitive component of the cable. And so again, the resistive it's going to swing one way. Over time, it's going to become more resistive than it is capacitive. Remember, brand new cable, pure capacitive. But over time, more loss, more inefficiency going this way. And yeah, actually, that's a great question because I can show you on the other side of eventually what happens when this cable becomes far more resistive, right? Then it's going to swing all the way over here and then be close to failure. And so you, as the NETA qualified technician, right, by being able to calculate this tan delta, you'll say, okay, what are we willing to accept as far as this value when we know it's too far towards failure, right? And so that's why the tan delta is important. So that's an excellent call. And we're going to take a look in our NETA book as to what are your acceptable deviations in terms of tan delta. Okay. But yeah, excellent call because visually you can see that as the tan delta increases, well, what are we, or the customer willing to accept in terms of acceptable tan delta? Yep.
So is resistive and capacitance inverse relationships?
In this case,
One, they're always opposite of each other?
not quite, because we're looking in a phasor diagram here, Obviously, they share. If you were to do the cosine, then it would be the x-axis. If you're to do the sine, then it's the y-axis. But anytime it's not purely capacitive, it's not inversely in terms of linear trade-off, right? In this case, because they share axes, right? It'll have a non-linear relationship there. We'll try and take a look at some
So,
numbers
but
and see if
if
that's
capacitance goes down, resistance always goes up? Is that?
Yeah. They are.
That's what I meant. Like
Right.
one goes down, one goes up, till it's completely lost it. Total,
Yeah,
total
but it
charge.
would actually fail long before. It would still, have some capacitive component. It's not like when it's a pure resistor, then it fails, right? If you can see the future of electrical health equipment, then you're gonna make a lot of money. But in this case, NITA outlines, okay, what is an acceptable deviation when you test, different years at a time, right? You compare 5 years ago, 10 years ago, 15 years ago, that kind of thing. You'll say, okay, then it's about time that we replace this cable run or that kind of thing. But yeah, I think that answers your question. Yeah, but definitely it's a trade-off. They're on kind of opposite ends, but it's not like, okay, if this one is half, then this one's double. Not quite that.
So the diagram, it looks like the current stays the same for the initial, the current for the initial one, right? You're saying that current is caused by capacitance, the thing charging.
Purely capacitive. Like you could also say
Right.
I equals ICP here.
Yeah,
They're
and that stays the same over the life of the cable, or
we're treating the
changes?
current as fixed, I guess, because it is the vector sum of your capacitive and resistive component, right? So you can think of this I in magnitude, if you assign it a value of 1 or whatever, this is also going to be 1, right? It'll be 1 wherever it is. Whereas the ICP and the IRP will be the vector components of that, 1.
Okay.
We can get into it, right? It's just like your, what do you call it? Eli the Iceman kind of thing, for voltage leaks current or current
Yeah.
lines, whatever.
Yeah.
Like you have to fix something in order to determine the relationship. Like it's not gonna